Hi everyone, in this video I'm gonna give a brief lecture on Bernoulli equation and then solve an example. The Navier-Stokes equation is the governing equation of the motion of all fluids. And the Navier-Stokes equation with some assumptions can be simplified to the Euler equation. And then using the Euler equation, we can find the Bernoulli equation. And all of these equations are derived from the Newton's second law. So we have the Navier-Stokes equation on top of everything. Then by assuming that the fluid is inviscid and the flow is both incompressible and steady. We can find the simplified version of the Navier-Stokes equation, which is known as the Euler equation. And what do we mean when we say a fluid is inviscid? So we consider the motion of inviscid fluids for the Bernoulli equation. And it means that the fluid is assumed to have zero viscosity. And if the viscosity is zero, the thermal conductivity of the fluid is also zero, and there can be no heat transfer. So when we say inviscid, it means that the viscosity is equal to zero. And in practice, there are no inviscid fluids. But for many flow situations, the viscous effects are relatively small compared to the other effects. So as the first approximation for such cases, it's often possible to ignore viscous effects. And for the flow, when we say it's incompressible, it means that the density or rho is constant. And when we say a flow is steady, it means that the temporal derivative of any scalar property is equal to zero, which means that it doesn't change with time. And also the inviscid fluid flow is governed by the pressure and gravity forces, which is the Euler equation. And the Bernoulli equation is written on a single streamline. So the Bernoulli equation is the energy at each point. So the energy is P over gamma plus V squared over 2G plus Z is constant. So we can write it between 2 points on one single streamline. So here the P is the pressure. So here for the Bernoulli equation, P is the pressure, which has the dimension of Newton over squared meter, and gamma is the specific weight, which has the dimension of Newton over cubic meter. So P over gamma has a dimension of meter. So we can say that this Bernoulli equation is written as the heads. So again, the velocity, V is the velocity, which has the dimension of meter over second, and G is the gravity, and its unit is meter over squared second. So again, V squared over 2G will have a dimension of meter. So it's again head. And also Z, which is the elevation. And again, the dimension is length, which is meter. So each of these three terms has a physical meaning. So for example, P over gamma is the pressure head. But what do we mean by the pressure head? So it represents the height of a column of the fluid that is needed to produce the pressure P. So this is the head. The second term that we have here is V squared over 2G, which is known, V squared over 2G is known as the velocity head. And again, it's a vertical distance. But here, this vertical distance represents the distance that is needed for the fluid to fall freely from here, to fall freely, if it's going to reach velocity v here from the rest. So this distance would be the velocity head. And also z is the elevation head. Again, this is related to the potential energy of the particle, and we call it the elevation head. So here this is the Bernoulli equation that we have, which we can write it on a single streamline and between 2 points. So we can solve this problem to make things clearer. In here, the problem says that water flows steadily through the variable area horizontal pipe. So it's water, and water is an incompressible fluid, and it says that it flows steadily. So we have the steady flow. And the centerline velocity is given. Here we have the equation for the centerline velocity. And the viscous effects are neglected. So it's inviscid. Now we have all the assumptions for the Bernoulli equation. And the problem says that if pressure at section 1 here is 50 psi, determine the pressure at section 2 here. So for this problem, we can write the Bernoulli equation, and we can write it between 2 points on a single streamline. So we can write it between these 2 points. So the Bernoulli equation is P over gamma, and we're writing it for point 1. So the energy at point 1 is P1 over gamma plus V1 squared over 2G plus Z1. So this is the energy at point 1 and is equal to the energy at point 2, P2 over gamma plus V2 squared over 2G plus Z2. And here in this problem, you can see that Z1 and Z2 has the same elevation. So here, Z1 and Z2 will cancel each other out. And now we have the pressure at point 1, which is given as 50 psi, and we can find the velocities at sections 1 and 2 from the equation that we have. So the only unknown is P2, and we can find it from the Bernoulli equation. So let's write it. So for V1 is the velocity at point 1. And here point 1, x is equal to 0. So if we put x 0 here, it will be 10 times 1, which will be equal to 10. So V1 is 10 feet per second, and it's in the I direction. So it's in the x direction. And also V2, velocity at point 2, we need to know what is the value of x here, and it's given as 3 feet. So x2 is 3, and we need to put x equal 3 here, so the velocity would be 40. So V2 is 40 feet per second. So now we can write the pressure there. So we had P1 is equal to 50 psi. And here P is pound, S is square, I is inches. So it means that it's equal to 50 pound per squared inches. And also we know that the specific gravity of water is equal to 62.4 cubic feet, pound per cubic feet. So now we need to substitute these values into the Bernoulli equation that we have here. So P1 is 50 psi or 50 pound per squared inch divided by gamma, which is 62.4 pound per cubic feet. But now here we need to convert inch squared to the feet squared. And we will do that by the conversion rate. So we need to convert each inch squared to feet squared. And we know that 144 inch squared is equal to 1 feet squared. And now you can see that these 2 inches squared will cancel each other out. And on the denominator, we will have pound over squared feet. And in the denominator, we have pound over cubic feet. So this fraction will have dimension of foot alone. So this was P1 plus gamma. And then we have V1 squared over 2g. V1 is 10 feet per second from here. So it's 10 feet per second. And it's squared. And it's divided by the gravity. And it's equal to P2 over gamma. Well, we don't know the value of P2 divided by gamma, where gamma is 62.4 pound per cubic feet, plus V2 squared over 2g. Again, we have the V2 as 40 feet per second squared over 2g. It's 2 times g. 2 times 32.2 feet per second squared. So again, as you can see here, we have foot squared divided by second squared. So the second squared and second squared will cancel each other out, and the remaining unit will be foot. And here, similarly, we will have only foot. So here the pressure that we find from this equation will be pound over square foot. And we need to convert it to PSI. So at the end, pressure at point 2 will be equal to 39.89 psi. So that's the solution of this problem. Thank you.